opening the doors in 5, 4, 3, 2.
Good morning. Folks are starting to roll in. I'll wait a minute or two to get the majority of people online. We had good registration for this particular webinar, and so I want to make sure that before we start, we get the bulk of the people, get everyone in. And we'll start in just about half a minute. Okay, it looks like we're over 40. I think that's a good place to start. Good morning, everyone. Welcome to today's Future Supply Action Funding Program webinar. I'm Warren Teitz. I'm a team manager within Metropolitan's Water Resource Management group, and I'm the program lead for the Future Supply Action Funding Program. I'll also be your moderator for today's webinar. We're going to get started shortly, but first, a few housekeeping items. We are recording this webinar, so please keep your mics and cameras off. We will be posting the slides, webinar, and final report on our website in the near future. So this is a double header. We have two presentations for you today, and we hope to get questions at the end of the both presentations, but we might take one or two questions after the first presentation, time permitting. Please type your questions in the Q&A or chat box, and we'll get to them as time permits. Next slide, please. So we're going to start with just a brief overview of the Future Supply Action Funding Program and Metropolitan, get into the first presentation, which will be with the City of Fullerton and Orange County Water District. We'll take a couple of questions, then we'll get into a presentation on Eastern Municipal Water District, and when they're concluded, we will take questions and answers again as time permits. Next slide, please. So first, a quick introduction. Metropolitan, most of you know who we are. We're the nation's largest wholesale imported water supply. We serve 19 million people, a $1 trillion economy, and 26 member agencies is who we sell our water to. We import water from the Colorado River through our aqueduct and also through the State Water Project. Next slide, please. But over the past 30 years, we've been on a journey on diversifying our supply resources with over $1.5 billion invested in storage, in transfers, in conservation, in local supplies. And that's the purpose of the Future Supply Action Funding Program, is to advance local supplies within Southern California. Next slide, please. So we established our Future Supply Action Funding Program in our 2010 Integrated Resources Plan with the goal of driving innovation in local supplies. That includes groundwater supplies, stormwater supplies, reuse, and desalination. And the goal of the FSA program is to partner with our member agencies to pilot new approaches and technologies, remove barriers to supply development, and those barriers include institutional barriers, technological barriers, financial barriers, and regulatory barriers. And finally, one of the key principles of the Future Supply Action Program is that even though these studies are for a particular agency, they're really meant to benefit the region, and we hope to get the word out by sharing the results of these studies through webinars like this. And so benefiting the region is a core principle of the program. Next slide, please. Our current program includes 14 studies that we've partnered with our member agencies, totaling just over $3 million, and they cover all 4 of the resources. The presentations we're going to hear today both cover potable reuse. We also have 7 studies that we've co-funded with the Water Research Foundation. That includes 6 potable reuse studies and 1 agricultural reuse study, just under $1 million. So the total program is about $4 million. And so I think we can go to the next slide, please. So our first presentation is from the folks from OCWD. They partnered with the City of Fullerton Our first presenter is Megan Plumley, Dr. Megan Plumley. She's the research director for the Orange County Water District. And joining her would be Dr. Julio Polanco. He's a postdoctoral research associate also with the Orange County Water District. And at this point, Megan, I'll turn it over to you. Thank you.
Thank you so much, Warren. Hopefully everybody can hear me and I got my camera on. All right, so the title of our presentation today is Demonstrating Virus Log Removal in Potable Reuse to Increase Regulatory Confidence. Hold on, let me minimize my thumbnail there. I can't see my own slides. Okay, there we go. So I'll start with some quick acknowledgements. So of course, our funding sources, so funding from the Metropolitan Future Supply Actions Program that Warren just introduced. And I especially want to acknowledge the City of Fullerton, who is the MET member agency that sponsored this project so that we could complete this work in collaboration with them. We also had additional funding from the Water Research Foundation and the United States Bureau of Reclamation, or USBR. And the USBR component helped fund the RO LRV portion of the study, where we partnered as well with Trestle Technologies. And then of course, for the wastewater LRV evaluation part of the study, our partner, the OC Sanitation District, their staff and their laboratory were instrumental in doing this big project. So our outline for this brief presentation, quick background on OCWD, and then each of our two studies, the pathogen LRV study for the OC sand wastewater treatment process, and then the reverse osmosis process. All right, so Orange County Water District, we were formed in 1933 to manage the Orange County groundwater basin, this large aquifer that underlies the region. We also protect rights to the Santa Ana River. And we provide groundwater, so we function as a groundwater wholesaler to 19 different municipal and special water districts. So they support about 2.5 million residents in the region shown there on the map. So this groundwater supply is really important. It provides about 77% of the water supply for North and Central Orange County. And to keep up with that demand, we do groundwater augmentation. So we replenish the groundwater via spreading ponds in the Anaheim region and also injection wells as part of a seawater intrusion barrier closer to the coast. So as part of this water supply portfolio for groundwater recharge, we operate an advanced water purification facility that we call the Groundwater Replenishment System, or GWRS. It's been in operation since January 2008, and it's the largest potable reuse facility in the world currently, making about 100 MGD. And we're in the process now of expanding the plant up to about 130 MGD production to be completed in 2023. So this, the current 100 MGD is equivalent to 103,000 acre feet per year source of water. So that's enough water for about 850,000 people. So this project reclaims treated wastewater from the Orange County Sanitation District. It's a secondary effluent that they produce that we then advance purify, which would otherwise be wasted as discharge to the ocean. So we purify it and then recharge it into our groundwater basin for drinking water supply. So a quick overview of the treatment process. On the next slide, I'm going to show the pathogen LRV credits that we demonstrate for each step. So I wanted to quickly go over the steps themselves. So of course, the first treatment process is the Orange County Sanitation primary secondary treatment process on the left there. That serves as the feed water to our microfiltration process. We also are transitioning over to ultrafiltration, so have a mix of both membrane types in the plant currently. And then the reverse osmosis process. Finally, the ultraviolet light advanced oxidation process. And then this water is either sent to Anaheim for the spreading ponds or used in the seawater into injection wells for the seawater intrusion barrier. So this table, I know it's a little bit dense, I'll walk you through it, but this shows our pathogen LRV credits that we currently achieve across the treatment process. So in the first column there on the left is the requirements. So for potable reuse in California, we're required to demonstrate the 12-10-10 rule. So 12 logs of virus removal and 10 logs for Giardia and Cryptosporidium. And what that means is, first of all, it's referring to treatment from the influent to the wastewater treatment process. So that's the raw, sewage coming into OC sands process from that water source all the way to the water that is pumped out of the aquifer, so drinking water production wells. And then what the logs refer to is like a percent removal. So 12 logs removal of virus means 99.999% removal. It has 10 nines after the decimal, so a high degree of removal. And then each of the columns in the table shows each treatment process with the logs demonstrated. You add it up to achieve the total logs. So you can see that for Giardia and Crypto, if you focus first on the black colored numbers, so that's our current demonstrated LRVs. So you can see for Giardia and Crypto, we are required to meet 10 and we're achieving 12 plus. So we're comfortable there. But the driver for this project was really to demonstrate increased virus credits. You can see that currently we get no credits for the OC-SAN wastewater treatment process and only 2 credits for the RO process. So this comes out. So we're really pretty dependent on that underground retention time. The additional 4 logs, we get 1 log of virus removal per 1 month of underground residence time. So we're meeting the 12. The plus refers to the fact that across the RO process, the pathogen reduction is demonstrated through TOC removal via online monitoring. And on a given day, maybe the average is 2.1 or 2.2 logs. So that's why it might be 12.1 or 12.2 logs for the total. So it's a little close to the 12 logs requirement. So the motivation for this project was really to increase our credits across the process for virus, such that we'd have more of a safety factor or a buffer there on the total credits met, but also be less dependent on underground retention time, which could allow us in the future to do the potable reuse recharge or groundwater augmentation at locations that are new locations available to us closer to certain drinking water production wells. So we wouldn't have as many logs underground. So the green numbers show the outcomes of our study we're presenting today. We are, based on the results of this study, proposing to our regulator, Division of Drinking Water, a 0.7 log for the OC-SAN treatment process for virus, and then an extra log for the RO process. Both of these are being currently reviewed by DDW as part of our Title 22 engineering report for the final expansion of the plant. So still under review, but this is what we're proposing based on the study today. So with that, I will turn it over to Julio, and he's going to present an overview of the results from our OC-SAN virus LRV study.
Thank you, Megan, for that introduction. Can you guys, am I coming through?
I can hear you.
Okay, great. So thank you everyone for joining us this morning. I'm pretty excited to show some of the data for this study. So as Megan mentioned previously, the Orange County Water District's groundwater replenishment system currently receives a blend of 3 parallel treatment processes from the Orange County Sanitation Plant number 1. These 3 parallel processes include 2 activated sludge, or AS1 and AS2 treatment processes, and 1 trickling filter process. So what the trickling filter process is a simple aerobic wastewater treatment process that removes organic material from the influent wastewater stream. And the activated sludge processes basically it's a nitrifying, denitrifying, partially denitrifying process that is more efficient at removing this organic material as well as some suspended solids. So after the GWRS final expansion, which is scheduled to complete in 2023, the GWRS will also be receiving a 4th secondary effluent supply of water that is from the Orange County Sanitation District Plant number 2. That is about 4 miles south of the current GWRS facility shown on the map right there. This treatment facility, or this treatment process, is a trickling filter trickling filter solids contactor, which is essentially very similar to the Plant 1 trickling filter, except it has an added step that is allows it to remove an additional amount of suspended solids and has improved organic material removal. So at the moment, as Megan mentioned in that previous table, the Orange County Water District currently receives no virus log removal credit for the wastewater treatment portion. And this study specifically focuses on obtaining virus credit, log removal virus credit for viruses specifically, not seeking additional Giardia or Cryptosporidium credit. Next slide, please. So some of the one main objective of this study was to obtain, as I mentioned before, propose a log removal credit for the wastewater treatment process. We can break that down into four distinct objectives. The first one being to quantify the viruses and other microbial targets within the raw influent and secondary effluent processes that I just mentioned for plant number 1 and plant number 2. And we did this over 24 sampling events, which I'll show in a moment. Second objective is to take this data that we obtained from the 24 sampling events, this concentration data, and calculate a log removal value for each treatment process independently. We did this using log normal statistical modeling techniques, which include a covariance approach and a Monte Carlo simulation approach, which I'll get into in a few slides. The third objective was then to go ahead and propose a 5th percentile virus log removal credit based on the statistical techniques that we considered. And alongside with this 5th percentile credit proposal, we will also be proposing a conditional operating range value. This is a set of basically parameters that describe the function, how the Orange County sanitation plant is operating, which represents a normal operating envelope. Next slide, please. So throughout this study, we monitored these viruses using a few standardized methods, including EPA 1615, both for the infectivity culture using the infectivity culture assay and the molecular assay. So I'll refer to the infectivity culture assay as the cultivable virus data set going forward. For the molecular data set, we used droplet digital PCR as opposed to the qPCR, which is within the modified 1615. We also used EPA 1602 to enumerate male-specific and somatic colophage by cultivation methods. And we also used the standard methods 9222B and D to enumerate total coliform and fecal coliform. Next slide, please. So here is some concentration data from the cultivable virus data set. On the y-axis, you'll see the most probable number per liter, which is obtained from the infectivity assay, which is also on a log scale. On the x-axis are the sample dates in month and year. What we can see here is we've plotted the raw influent data set for plant 1 and plant 2 as the black dots up above. And what you'll notice immediately is that, so if we focus, so what I'm also plotting are the secondary treatment processes, right? The concentrations we observed for those treatment processes. And we can see that the activated sludge 1 and 2, shown in the blue diamond and blue squares, have relatively low concentrations, right? So this, compared to the black raw influent data set, we can see that these lower, that suggests that there's removal throughout the process. And if we look at the trickling filter data sets, which are the dark green triangles and the light green triangles for plant 2, we also see reduction after treatment when compared to the raw influent data set, which are the black points again. And what's so one thing I wanted to mention as well is that we didn't observe any non-detect measurements for either the influent or the effluent, which is great because there's no substitutions going on here. And what's most important about this particular plot is that on every given day that we sampled, the treatment processes show that there is log reduction or removal of these viruses. Next slide, please. So one way to visualize that data set, because it could be pretty daunting to see that kind of variability and trying to make sense of it, we can plot this on a probability distribution, which I'm showing here on the right. So to do this, what we do is we take those concentration values, which you see on the y-axis, again in log scale, and we can plot this against an x-axis that is a percent of values or a probability percentile. And what we can then see is a nice clean line, right, that represents the distribution of a given data set. So in the black dots, again, you'll see the raw influent. This is just for plant 1. And we could do the same analysis for the secondary treatment concentration distributions. And we can visually see when comparing to the raw influent, the reduction in concentration, right? So this reduction in concentration can be indicated or is represented by that pink arrow there. And yeah, so next slide, please. So considering this, visual representation of how to removal of these viruses, how do we quantify it? So we considered 3 different approaches for calculating log removal for each treatment process. The first approach we considered was same-day pairing. This approach basically assumes that the same water parcel is sampled from influent to effluent. And due to the complexities of some residence times in each that vary between each treatment process, it's kind of difficult to get a very accurate estimate. And this is largely not valid if we were to consider this approach. So we sort of pushed this aside. The second approach we considered was the Monte Carlo approach, which is essentially a computer simulation that is an iterative log removal estimation based on the influent and effluent statistical parameters. What this means is that the two distributions in question, for example, a raw influent data set and an effluent, are assumed to be independent. The third approach we considered was a covariance approach. This approach is a parametric evaluation of influent and effluent distributions that tests the variance of 2 dependent populations. So based on some review, based on the review from our GWRS IAP independent advisory panel, it was recommended that we proceed with a covariance approach based on the quality of the data set. Next slide, please. So proceeding with the covariance analysis, what we can do is to visualize this data, we can generate a similar probability distribution as I showed earlier, but with the output or the result of LRVs. So that's what I'm showing here on the right. So now you'll see on the y-axis, that is the log removal of cultivable virus. And on the x-axis, we have the percent of values for probability. So what I'm showing here are the 5th, 50th, and 95th percentile log removal values for each treatment process using the covariance approach. In the orange box, you'll see the 5th percentile values. And as you can see, the lowest log removal value we can see is for the plant 1 trickling filter effluent, which is at 0.74 log. The LRV distributions for plant 1 activated sludge 1 and plant 1 activated sludge 2 processes are higher than those of the plant 1 trickling filter and plant 2 trickling filter solids contactor. And this is consistent with the concentration values that I showed previously. So the covariance approach was recommended since this approach assumes and tests the correlation between the log influent and log effluent values. Next slide, please. So here I'm just showing a summary of microbial LRV results. This is a bar chart showing the 5th percentile values for each treatment process. You can see that on the x-axis, plant 1 trickling filter through the plant 2 trickling filter and the plant 1 activated sludge treatment processes. On the x-axis is the virus log removal. So what you can see here is for both plant 1 trickling filter and plant 2 trickling filter. I'm also plotting the 5th percentile values for somatic colophage and male specific colophage, right? And comparing that with the cultivable virus LRV that I showed earlier. What we can see here is for both colophage targets, the plant 1 trickling filter 5th percentile values are the lowest, and as well as the trickling filter from plant 2. And this also is consistent with the data we saw earlier as far as efficiency of each treatment process. Next slide, please. And to summarize some of the findings for this study, the covariance approach for determining virus log removal value credit was recommended by the GWRS Independent Advisory Panel. Due to the complexity of calculating a combined or amalgamated estimate of removal for all of the Orange County Sanitation District treatment processes, the 5th percentile value of the least effective treatment process, that is the plant 1 trickling filter, was chosen. And yeah, so this value was chosen as a proposed credit value to represent a conservative value, right, for all of the plant 1 and plant 2 processes, or the single plant 2 process. And finally, this proposal or this value is pending DDW review of the LRV calculation options. Currently, OCWD is proposing a log removal value for virus of 0.7 log, in addition to conditional operating range values for the Plant 1 trickling filter into the Title 22 engineering report. I believe this is the last slide. Next slide, please. Yeah. And with that, I'll just pass it back to Megan to talk about our RO-LRV study.
All right, thanks, Julio. Okay, so for this portion of the study, again, let me minimize myself so I can actually see my slides. There we go. For this portion of the study, focused on the RO process, so quick reminder of the background. What we currently achieve is about 2 logs of virus log removal credit across RO. That's granted based on TOC, or total organic carbon, online monitoring. So we have monitors on the RO feed and monitors on the RO permeate. You simply calculate the daily average TOC percent removal, which is around 99%, or 2 logs, and that is applied as the credit obtained that day for virus removal. So the objective of this study was to identify some alternative constituents that could be easily monitored, either via online monitoring or grab sampling, that would show a higher log removal value. So something higher than the TOC value of around 2. And I should mention, we also monitor electrical conductivity as a backup to TOC. So that achieves around 1.5 logs removal. So we wanted to do this over multiple months to make sure we demonstrated values that were representative over time in different seasons. And we wanted to do this at full scale, utilizing one of the full scale RO units within the facility. So that's a photograph there. Each of those distinct sections of white pressure vessels is a 5 MGD RO unit. So we have currently 21 of those in the facility. And then as far as the constituents we focused on, based on past studies and literature review, we focused on the 5 shown here. So we focused on sulfate monitoring in the RO feed and permeate, and strontium monitoring. So those are each naturally occurring ions that not spiked, but just naturally. None of these were spiked. All of these are compounds that naturally occur in the RO feed. ATP, adenosine triphosphate, is a biological molecule that's found in all living cells, but it's also, as a result of the wastewater treatment process, been lysed from the cells, and it's simply a compound that you can detect in the free in the water. So free ATP was used in this study. And then fluorescence, specifically peak C, is a measure of, or it's another type of measure of organic carbon, specifically fluorescing components of the organic carbon mixture, and a fluorescing in the band referred to as peak C. And this had been in the literature and some other studies looking at as a potential surrogate for RO integrity, similar to measuring TOC. And then finally, we also looked at nanoparticles based on some advances in detection technologies, including capabilities to measure online. I won't talk more about nanoparticles today because that was the one that didn't really work out in our study. The instrumentation sensitivity isn't quite ready yet for this type of application. But for the other 4, we did see promising results in every case. So this is a summary of our findings for the different constituents. Strontium showed the highest study average log removal value across RO with a value above 3. Sulfate and free ATP were close to 3, also significantly greater than the TOC and electrical conductivity that we monitored in the same full-scale RO unit at the same time. And then fluorescence peak C showed the lowest log removal average value, but still fair bit greater than TOC. The strontium and sulfate were all measured via grab sampling. However, since the time that we completed this study, online instrumentation has become available, and we're considering use of those. And then the free ATP and fluorescence peak C already have continuous or online monitors available. So that's what we used to collect the data for this study. So in the interest of time, I'll just quickly show you some data from the case of strontium and the fluorescence peak C. So for strontium, just to walk you through this chart, we had 3 different sampling events shown on this graph on different dates where we took an hourly sample because we were simulating, wanted to know, what would the data look like had it been an online monitor. And the RO feed concentrations of strontium are shown on the secondary y-axis on the right in yellow, because it's quite a bit higher than the RO permeate concentrations shown in green on the other y-axis. And then each hourly LRV is calculated and shown in the blue line there. So first off, you might notice that the strontium concentration in the feed is very, very flat and stable. We really didn't see any variability. And this was true for the sulfate data as well. The sulfate plot looks just like this one. And so for strontium, the average across these three events was an LRV of about 3.3 with a minimum on a particular hour of about 3.0. We did have a few non-detects sometimes in the RO permeate, and that's plotted as an open square. And in those cases, the method reporting limit, or MRL, is substituted for the permeate value, which is a conservative approach for estimating LRV in cases of non-detects. So the fluorescence data is interesting to look at because it does have much more variability than the strontium and sulfate, and ATP was the same. So ATP and fluorescence both showed a diurnal signal every day, up and down, having a peak around the same time each day. So it's a little hard to see because it's zoomed out here, but each of these peaks in that yellow RO feed concentration that you can see there, each peak is it's a diurnal signal. And then that behavior propagates to the much lower RO permeate concentration, and as well as the LRV value. So we do see some variability in the LRV based on the diurnality. So the average in this case, as I mentioned, was about 2.7 log removal value for fluorescence. And this data was measured every second. So the graph is actually showing each graph data point is a 15-minute average of the 1 second measurements. And we wanted to highlight this, even though it was the lower LRV of the others looked at in this study, because it fluorescence peak C is the monitor is pretty inexpensive and really easy to operate. So by far it was the easiest, online constituent to measure and demonstrate log removal value, even less finicky than like a TOC monitor for sure. So it's I think for a facility interested in perhaps a new facility coming online interested in demonstrating integrity, but perhaps not wanting to have the expense or complexity of online strontium, sulfate, or ATP, which are more costly. This could be, a candidate to pay attention to. So findings overall, we really saw that these novel online methods are becoming more feasible to enhance RO-LRV credit based directly on this project outcome. OCWD is moving ahead, working with our regulator to propose a tiered framework. We couldn't pick just one, so we created a tiered framework based on strontium, sulfate, and ATP to be monitored in our facility as alternatives for demonstrating RO integrity related to our engineering report for expanding our facility and the permit there. We would still keep TOC and electrical conductivity monitoring as backup, and because these provide other, water quality monitoring value. So it's really exciting to see how the findings from this study, not only for the RO portion here, but also the wastewater portion that Julio presented, immediately being able to translate this into a direct application for our facility. And just want to note that though we are an indirect potable reuse facility, these findings are equally applicable to direct potable reuse facilities that are going to be required to demonstrate even higher pathogen log removal values. So with that, if we have time, there may be some time for questions, or we'll move to the next presentation.
Great, Julio, Megan, great presentations. We have time for one question, and we actually have one question. And so I think we'll answer this one live. This is from an anonymous attendee. And I think, Julio, this is directed for you. What would you estimate as the ballpark sampling cost for the wastewater treatment plant LRV study? So for basically the first part of the presentation.
Mm-hmm. It's a good question. It can get pretty expensive very quickly. For our study, we have some pretty large invoices, especially because we considered using molecular approaches. But on an average, I would say we looked at about $500 cost per sample for the enteric virus analysis, the cultivable assay. If you're looking at a 24 sampling event for one treatment process, that translates to about $12,000 to do that assessment. And regarding the coliphage and Untitled coliform, we were lucky enough to have the Orange County Sanitation District help us out with that. but we have about $100 for a cost for collapage analysis for both targets.
I can jump in and add, we were just trying to put these costs together for a new Water Research Foundation project that's developing guidance for demonstrating pathogen LRVs across wastewater treatment plants. So I encourage you all to watch out for that one. The PI is Professor Verbila, but I don't recall the number of the project, but I believe he's pulling together costs from multiple projects, including ours, and the average is something like $200,000 to $300,000 in total to do a pathogen LRV study across. But I think that's including like Giardia and crypto as well, whereas we just did the virus. So that's kind of a ballpark number.
All right, terrific. You know, for the sake of time, I think we'll just leave it at that one question. We'll have additional questions for Megan and Julio and time to ask them at the end of the next presentation. So why don't we, David and Christian, why don't you call up your presentation and we'll get on to the next to Eastern. And so our speakers for the next presentation are David Alice. He's a principal civil engineer with Eastern Municipal Water District. And then the consultant, Christian Sanders. He's an environmental engineer with CDM Smith. David, I'm going to turn it over to you and we'll see you at the end.
Okay, thank you, Warren. Okay, go ahead, next slide.
Yeah, okay, give me a second here, just make sure that I can, okay.
Drive it. Okay, the name of our study was the EMWD Brine Minimalization Pilot Study. And so what we did was we utilized Ccro, closed circuit reverse osmosis, to try to maximize recovery. But first, I'm going to talk a little bit about Eastern. Again, we are one of the member agencies of Metropolitan Water District. We cover the area from Moreno Valley down to the Temecula Valley, so the Inland Empire district. And we are the 6th largest utility in California. The numbers, we were established in 1950. We're full service. We do water, wastewater, recycled water. We do both wholesale and retail for our water. Our population's growing quickly. We're at a little bit over 839,000. I said large, we're 555 square miles is our service area. And then really important is we're only 38% built out. So we have a lot of growth potential within our district. Like everybody, we're trying to diversify our supply portfolio. So 30 years ago, you can see on the left, majority of our water was imported from Metropolitan, both through the state and the Colorado River Aqueduct. And then we're fortunate we have a large potable water aquifer that supplies drinking water. And so it was about 18% 30 years ago. And then we've had a recycled water program for a long time, and we've been recycling water. Moved to today, and we pump less potable groundwater, but we've started as a percentage, but we've instituted a new program where we have pumping the brackish basins. On the west side of the district, the groundwater aquifers are brackish. And so we have about 8 million gallons a day in desalter capacity. And those desalter plants are hooked up to the inland brine line. And then we continue to expand our recycled water program to the point where we're utilizing, on average, all the recycled water, all the wastewater is treated to Title 22 standards, disinfected, and then used for non-potable sources. Next slide. Okay, so the district has created a program called Groundwater Reliability Plus program, and it has 7 sub-projects to it. Today, I'm just going to talk about the top 3 here shown, and these are groundwater recharge projects. So the first one, the groundwater sustainability, that's our current groundwater recharge that we do with imported water from the state via Metropolitan. We have an agreement with both Met and the Saboba Indian tribe to recharge on average 7,500 acre feet a year. And so we do that in existing recharge basins in the San Jacinto River. And then the middle project there, our water banking. This is a new initiative that we are going to bring in more imported water and increase the amount of recharge that we do. And we just finished construction on what we call Mountain Avenue West Recharge Basin. And so it's a basin that has a capacity infiltration rate of about 30,000 acre feet a year. And so we'll be bringing in more imported water. We're currently working with Met for a new connection and a new 60-inch pipeline to be able to bring in additional up to 14,000 acre feet a year of recharge water. And then on the right is our indirect potable project or groundwater augmentation project. We're titling it Purified Water Replenishment Project. So this is a new potable reuse project that will take the treated wastewater and recharge it into the San Jacinto upper pressure zone basin. That next slide. So a little more detail on our groundwater augmentation project. So again, I mentioned all the flow comes from our San Jacinto Regional Water Reclamation Facility. So we'll start with the disinfected tertiary. That water will have two streams. The main stream will come through a MFRO system, and then it will be sent out to the recharge pond. And again, all we're not asking for any credit on the 10, 10, 12 through the MF and advanced treatment process. We are permitting this as a tertiary groundwater recharge project. So all our credits are from the Title 22 disinfected recycled water treatment, and then the soil aquifer treatment and the groundwater retention. The reason for this treatment is the groundwater basin there has a maximum benefit. So to comply with the basin objective plan, our recycled water currently is about 600 TDS, and the maximum benefit objective is 500 TDS. And the current water in the aquifer is probably around 400 TDS. So we want to recharge water that is higher quality than that is in the existing groundwater there. And then based on seasonality and availability. So right now, I said we're almost 100% subscribed to our non-potable water. We have agriculture is our major component of users. So, but in the winter, when it rains, we do have extra recycled water. So we're going to supplement the water on a seasonal basis. So we'll put some Title 22 water in the recharge basin in the winter, and in the summer when the non-potable demands are high, we'll only recharge the advanced treated, the MFRO recycled water. And then with the import water, that all gets blended into our recharge basin, our new Mountain Avenue West. We did the groundwater modeling, and it shows that it takes over 5 years to reach the nearest potable water well that Eastern owns. Next slide. All right, so this is the project. So again, the location of this project is out east in the San Jacinto Valley. We are over 20 miles from the brine line at our desalters. So brine management is a #1 issue out here for us. We're proposing on using brine evaporation ponds. So we want to try to minimize that brine flow as much as possible. And so we've been looking at different methods, and this is where we came with the pilot project of how much could we do recovery. And we lost the screen, but I was going to turn it over to Christian from CDM Smith, and they were our partner on the pilot study.
Yeah, Dave, I had another version up and it was going to play something. So I'm going to have to reload that file because there was no way for me to basically reset what was being shared. So just give me 1 second. I apologize to everybody on the call right now. It won't take long. Almost there. Okay, I'm going to share my screen. I'm going to scroll down. Okay, hopefully, Dave, is that coming through on your side correctly?
Yes, it is.
Okay, I apologize for that. Okay, so thank you. So we just wanted to start off first with just a brief introduction to the pilot. So really the goal of this pilot was to look at how high recovery we could achieve with the process. And again, being an inland location, brine disposal is a major cost and project driver for this project. So the preliminary design was done a few years ago by CDM Smith. A traditional 3-stage RO was proposed at the time based on 92.8% recovery. And the objective of this pilot was really to look and see whether or not we could push that recovery up a little bit higher using the CCRO process. So the district procured an MF pilot from Wigan, and that's shown here. And they were leasing the Desalitec pilot here, shown in the back. And we were pulling feed water out of our chlorine contact basins here located behind the facilities, and it's a partially nitrified tertiary effluent. So another photo for the backside, we've got our CCRO pilot here on the right-hand side. We've got the MF pilot on the left. This MF filtrate tank was our balance tank between the two pilots. So we produced filtrate, which was used for backwash in the MF and was the feed water supply for the CCRO. Now the CCRO's chemicals were located outdoors, but the MF's chemicals were located inside the trailer. All the product water that we produced, the brine and everything else, was returned back to the chlorine contact basins via this waste sump here. So a quick schematic for those of you on the webinar that are not familiar with CCRO. It looks similar to RO, but the main difference is this circulation pump and the brine flush valve. So during the closed circuit cycle, which is the cycle where we're producing permeate as a normal RO, but we're also recirculating brine. And in that process, the recovery is slowly increasing over time during the closed circuit cycle. Now, once you hit your recovery value, in this case, we were targeting a value of, we started the pilot study at 90%, and we were trying to push it up to as high as 95. When you get to that recovery set point, what happens is the brine flush valve opens and the circulation pump sends concentrate to waste. And it's during that cycle, the plug flow cycle, that the CCRO is functioning as a typical RO. Now, during both these cycles, the permeate flow remains unchanged. It's the concentrate flow that's either purged during a plug flow cycle or is recycled during the concentration cycle. And it's that concentration cycle that's really unique to CCRO. So in the interest of time, we won't dwell too much on the MF for this. The study didn't really focus on the MF, but we thought it'd be important to present some of the key design parameters for the MF. For those of you who are interested, we used Torres TIPS membranes. We used 200 micron auto strainers upstream. And we had the ability to dose sodium hypochlorite, liquid ammonium sulfate, and sodium bisulfite, and we would vary those depending on changes in the feed water quality. Just a couple quick views of the inside of the MF pilot container. You can see this is one of our MF trains here. It was 4 membranes. Now this pilot had the ability to test different membrane combinations. That was beyond the scope of the pilot study. We simply focused on one. And but as I said earlier, the district did procure this pilot and has that ability to test in the future if they're interested. Some of the key operating details for this MF pilot. Now, unique to this pilot, we were operating with a constant level control as opposed to constant flow control. So that resulted in a variable flux rate. And you'll see that later on when I present a little bit of data on the MF. But 9 to 26 GFD, so very conservative. Again, the objective here was for the MF to really be an out of sight, out of mind process that we didn't have to spend a lot of time operating, so that we could focus all of our energies on the CCRO pilot. So we started with a backwash interval of 45 minutes. We didn't change it at all throughout the pilot study, which was about 7 months long. And we, on average, we're doing a chemical enhanced backwash approximately every 14 days, which is, it's quite a lot of time between chemical enhanced backwashes. But we started off with about 1 week in between, and we found that we were getting very little decrease in permeability. So we stretched out the 14 days, and in general, this was sufficient. As you can see, that resulted in an overall system recovery for this process of about 98%. Some of the operating data, again, because we were operating with that variable flux, this is that red data here. It's quite messy looking, but here's our permeability down here in purple and our TMP in green. So you can see our TMP was really never much higher than 4 PSI. The permeability when we started off the pilot was around 10 GFD when it was clean, and we finished the pilot study was more or less at 10. So we didn't perform a CIP at all during this pilot study. The red lines indicate our chemical enhanced backwashes. We were seeing not the best chemical enhanced backwashes at the start of the pilot. We actually, figured out that was actually due to some airlocking in the sodium hypochlorite line, because we didn't dose sodium hypochlorite continuously. So we did have an issue where airlocks could occur. Once we were aware of that issue, we could address it prior to performing the chemical enhanced backwash, and we got better cleans as a result. Train 2, because it followed train 1 in the chemical enhanced backwash cleaning schedule, typically didn't have the airlocking issue, and as a result, its permeability stayed a little higher throughout the study. But again, that was what we showed here. And just to show, when we talk about stable performance, this turquoise line here is our permeability. Very little change from start to finish over a 24-hour period, and this would go on for days. TMP, roughly between 1 and 3 PSI, more or less, on average over a 24-hour period. And our green dots here are the flux. Again, because it's variable, it's a little scatter shot on the screen. So now to dive a little deeper into the CCRO process. Key design parameters for this one, we used DuPont's Fortilife membranes, and this was on the recommendation of Desalitec. It's their biofouling resistant membranes, 8-inch full-size membranes. We ran it at 10 GFD based on Desalitec's recommendations. We used a 1-micron cartridge filter upstream, and we had the ability to dose anti-scalant and sulfuric acid upstream. Some of our water quality constituents, we've got a red box around our phosphorus because that was the driver behind our anti-scalant selection and dose rate. This is also the driver behind our pH set point, calcium phosphate scale being the main concern we had. We did start with an Avista product. Ultimately, we about halfway through the pilot study, we went to AWC. We found that their projection software was more robust for CCRO. It's the only one that we're aware of that actually has a CCRO specific functionality to their projections. We also were able to do bench testing at their labs in Florida to confirm the findings from the projection software. It just gave us a lot more confidence in what we were using. So we settled on a dose of 12 milligrams per liter and a pH of 5 based on those worst case conditions. We only identified the worst case condition at the start of the pilot, but again, we're really concerned about having some uncontrolled scaling occur. And so we based all of our chemical dosing set points on worst case to make sure that any fouling that was happening was simply reversible fouling and not irreversible. So this is our long-term operating data. I'll show you the normalized permeate flow differential pressure on this one, and then a couple slides later, I'll show you the normalized salt passage, but it's really the normalized permeate flow that gave us our best indication that fouling was happening. So when we started off the pilot, we were basically trying to confirm that at 90% recovery and 92% recovery, everything was stable. So we're basically in this range till about day 60. We're not really operating the CCRO any harder than we probably would operate a 3-stage RO. And again, that was just to confirm stability of process. Once we did that and we were ready to start pushing it higher, we performed a CIP at about day 75. And after that, to make sure we had clean membranes, started to increase the recovery. So We first started at 93% and waited to observe some stability in the trends. Then we're comfortable with what we were seeing. We went to 94, saw a little bit of a decrease, but nothing too scary, and went to 95. And at 95, we definitely saw what we thought was a fairly consistent downward trend, and decided at that point to be conservative, let's perform a CIP and try again. So before trying again, that's when we actually switched to our AWC product. So about at day 111, we switched to the AWC product, put it online at 94% recovery, looked for some stability, and then went to 95. And at 95, we again saw a fairly steady decrease and performed a CIP again. Again, our concern here was that we were going to have some irreversible fouling occur. We didn't want to have the delay imposed by either needing to order new membranes or to perform consecutive CIPs. We really wanted to minimize any of that downtime. So we were performing CIPs on looking for decreases. Anything greater than 15% normalized permeate flow loss was a concern. So after the third CIP, we decided, well, let's go back and let's run at 94%. We haven't done that for an extended period of time. Let's run it at 94%. Let's see what happens. So what we saw is we definitely saw a steady decrease after this third CIP, but we thought this decrease might just be attributable to very clean membranes kind of stabilizing post CIP. And it did seem to start to steady up, to trend off at that point. And this blank period you're seeing after about day 135 is a situation where we ran out of antiscalant, typical snafu on a pilot study. We ran out of antiscalant, needed to order more, and needed to wait. And so we soaked the membranes and periodically refreshed that soaking during that time. Put them when we finally had our antiscalant back on site, batched up. Put the membranes back online. You can see there was a slight boost in performance after having sat and permeate, which would be expected. We let it run, and then we got a good, another 15, 20 days of running before we started to see a decrease again in the performance. And after about 38 days since our last CIP, we decided to clean the membranes. To confirm the repeatability of these results, we decided to run another run at 94%. And we performed a CIP, ran it again. And after about 24 days, we stopped the pilot because we had a number of maintenance activities occurring on the full-scale facility that were going to require the pilot to start and stop several times. We decided we had enough data at this point to be confident around the 94% was sustainable. So the pilot study that we were talking about today ended at this point in time here. So just a close-up of those last two extended runs at 94%. Unlike typical RO, because CCRO has variable recovery, what you end up with are bands of data. And what we've done here is we filter the data based on a range of 75% recovery to 95% recovery. And that's why we end up with these bands in data. But we were using these more close-up views to really understand what our trends were doing rather than that long-term data set, which is great when you're analyzing CIPs. But in terms of analyzing, how are you trending since your last CIP, the more close-up view is definitely more helpful. Again, you can see the differential pressure didn't really change much. Normalized salt passage did decrease, after we brought it online, which we would expect, but not a whole lot of variability. Maybe a slight downward trend during this first run, but not a lot during the second run. So normalized permeate flow is definitely our best indicator of fouling. So we did pull a membrane at the end of the first extended run at 94%. I'll just show you some photos. So these were some of the findings. So when they did the analysis, this is just a close-up of the concentrate end and the feed end. You can see everything is fairly clean. They did find a light foulant. I'll go back to that slide here. So their conclusion, everything was looking very visually good upon arrival. It didn't weigh very much compared to a brand new membrane, so it hadn't accumulated a lot of material. When they went to do their standard CIP procedures, which typically they perform a generic CIP and then they start to get into more specialty cleans to figure out what's the foulant, what they found was just soaking a coupon in deionized water in preparation for the CIP, they got a 20% boost in permeability over the membrane's nominal specification. They then got another fairly significant increase in the permeability after just doing a generic high pH clean. They then did the typical acid clean after that. There was a slight change, but not too drastic in that permeability. Overall, there had been an increase in they calculated approximately 45% increase over the membrane's nominal specification, which was very interesting. They looked at salt rejection as well, and when they normalized that for flux, it was within specification. So that large increase in permeability was not associated with oxidative damage, and because the Fujiwara test came back negative, and the salt rejection, as I noted, was within the specification. They didn't find any evidence of inorganic failing, which is what we were mainly concerned about, especially with the risk of calcium phosphate scaling occurring here. And so the foulant actually was determined to be organic in nature. They didn't provide much more information beyond that, but that simply was the only thing that was really could be understood by the autopsy results. They did conclude that the membrane was substantially more permeable than the membrane specification, which was simply an interesting fact that they uncovered. They did tell me that they've identified that from time to time, and the end conclusion was that we simply had something organic that we needed to focus on for the future. Now, we didn't get these results back to the end of our pilot study, so we really haven't had any ability to take any action on these results. It's simply information that came back at the end. So we did perform a cost analysis to look at what would a CCRO facility cost versus a conventional 3-stage for this pure water replenishment project, which is initially going to produce 2,000 acre feet per year based on 90% availability. The preliminary design that CDM Smith completed in 2018 assumed an average flux for the system of 12 GFD and a brine flow of 108 GPM. So if we could bring the recovery up to 94 with CCRO, we could bring the brine flow down to 89 GPM, and a 20% reduction in brine flow is fairly significant on a project like this. So some of the things we assumed when we did this basic cost analysis, we were only going to look at the CCRO and 3-stage RO equipment, chemical conditioning, and brine ponds. We were going to assume that all other project components were identical, and that labor costs were going to be equal. For the operating costs, we included power, chemicals, membrane replacements based on a 5-year average membrane life, and we assumed a flat 2% of equipment cost for maintenance. Now for that CapEx, we assumed there would be two MGD trains, and that was to have redundancy in the RO for the 3-stage RO option. We costed that at $2.4 million. And for the CCRO, we assumed 3 1-MGD trains. After talking with Desalitech, they thought the 1-MGD train was the most cost-effective for this project. So we based our assumptions on assuming that there would be 1 redundant 1-MGD train. That came out to a cost of $2.7 million, so a little bit higher than the 3-stage RO. Now, we did cost the brine ponds in the preliminary designs. That came out to 9.2. So we escalated that to 2021 numbers, assuming 5% escalation, which, as everybody knows in this current environment, may or may not be exactly accurate, but is more or less in the ballpark. We came up with 10.6 million for those ponds. Again, remember that number of 108 GPM. So when we did the MPV estimate for a 30-year MPV, we assumed smaller capital costs for the evaporation ponds related with the CCRO, and we basically just took a proportional reduction. So we 89 over 108 to come up with the value of 8.7 million for the ponds for a CCRO process. For annual O&M, again, as I noted, those are based on the chemical and power costs and an average membrane life replacement every 5 years. The cost is considerably higher for the CCRO because we were basing that on the numbers that we used during the pilot, which were very conservative. We certainly would expect that number to come down if we were experiencing a degree of optimization and average conditions. So this number came out to be $442 per acre foot for the 3-stage RO and $467 for the CCRO. We definitely would expect it to be less daylight between those two numbers based on a less conservative regime of chemical dosing for the CCRO. So some of the potential enhancement opportunities, as we noted, so during the pilot, everything was based on worst case conditions for phosphate, 15 milligrams per liter. We would definitely assume that there would be some significant savings based on a more average set of conditions. To achieve that, you would certainly need to have the monitoring in place to be able to make adjustments based on changes. So having phosphate analysis happening upstream, online analyzers located downstream of your tertiary filters in the case of the district's treatment process, making sure that the anti-scalant was based on 7.5 or somewhere in that neighborhood would certainly make a significant reduction in the cost of anti-scalant, which is very significant on these projects. And certainly CCRO technology opens up a lot of potential in terms of its ability to vary chemical dosing based on the recovery. We didn't explore that during this pilot study, but there's definitely some intriguing opportunities in the future for looking at changes in the code to adjust chemical dosing as recovery increases in time. During the first 30 to 50% of a CCD cycle, there's really no need for any pH adjustment. So that opens up a lot of possibilities, certainly something we didn't do, but would be very intriguing to look at in future CCRO piloting studies. To end with some observations and conclusions, again, as we noted, the MF operating parameters were very conservative, and as a result, we got very reliable performance out of that system, which was very nice. Allowed us to fully focus on the CCRO. Now, the CCRO was, showed extremely similar operating stability compared with a 3-stage process in the typical band where we would expect 3-stage RO to be operating on a feed water of this type, 92 to 93% recovery. We pushed it and we could get up to 94% recovery, assuming a 30-day interval between CIPs, and that's just a sort of a standard industry benchmark. We were being very conservative in how we triggered those CIPs. Again, we were looking for no greater loss than about 15% in the normalized permeate flow, but we acknowledge that many applications can go much harder than that. We say here 20 to 25, but up to 50% is not unheard of. If we had more time in our piloting study, we could have maybe taken those losses much higher if there wasn't as much of a risk of irreversible fouling affecting what we could achieve in our 6 to 7 month piloting window. So we'd say that reliable pH monitoring and control is critical, especially when you've got phosphate in your feed water. Redundant instrumentation for something like a pH probe would be highly recommended. The membrane autopsy was pointing towards organic fouling, which in the future would definitely suggest there definitely needs to be more attention to the chloramine residual through the system, making sure that you're doing analysis on the feed water constituents to make sure you're tracking and getting a better understanding of what that organic material is. And the 30-year MPV for the conventional 3-stage was less than the 30-year MPV for CCRO, even when you consider there would be smaller ponds. But again, as I noted, the daylight between those two MPV values would certainly come down. With a degree of optimization, we certainly think it could become much closer. So with that, we'll hand it over to questions.
Great. Christian, David, thank you for another terrific presentation. We had two great presentations today. Before we did get a couple questions in and more coming in. Before we do though, Christian, you used a lot of acronyms, which I'm very familiar with. I just wanted to make sure that folks that are participating understood what you were saying. GFD, TMP, I think were two ones that you used, and so if you could just tell people really quickly what those are, and then we'll get to the questions.
Yes, yeah, good point, Warren. So GFD, that's gallons per square feet per day. That's a flux value. So that's flow across the surface area. And so that's how we denominate the flow across our membranes with respect to the MFUF and the RO. The TMP is transmembrane pressure. So with MFUF, that's the pressure from the feed to the filtrate side of the membrane. So there's a pressure loss as you push water across the membrane surface. And we use differential pressure when we're talking about pressure differentials in an RO process. CCRO, closed circuit reverse osmosis. It's also sometimes referred to as CCD, or closed circuit desalination. And the closed circuit, again, is that what differentiates it from traditional RO is there's just a constant concentrate stream that you're producing that's going to waste, and you're producing permeate flow at the same time. With the CCRO, that concentrate stream is recycled back to the feed side of the membranes for a period of time until you've reached your recovery set point, at which time you purge the concentrate from the vessels and you refill the pressure vessels with new feed water, and you begin the concentration cycle over again.
Perfect, thank you. That was great. Okay, so we've got two questions, I think, for Eastern, and then we'll open it up to everybody for both presentations. The first one comes from an anonymous attendee, and their question is, I think, David, this is for you. What are the virus log removal values proposed for disinfected tertiary treatment, and for which processes? And I think they're referring to the pilot test you were talking about earlier.
Yeah, well, so we're taking credit for the Title 22 disinfected water that's produced at the regional water reclamation plant. So based on Title 22, for the filtration and the disinfection, we're taking 4 credits for virus removal. And then we get the 10 log removal for Giardia and Crypto via the Title 22 section. And then the underground retention time of, again, we just have a numerical model at this time, so you only get half the credit for per month, but we have a 5-year, over 60-month retention time. So again, we're not taking any credit for this MFRO treatment. So we're basing it strictly off the Title 22 section and the Title 22 non-potable water with the groundwater retention time.
Great, thank you. This next one I think is for you, Christian. Does CCRO save energy costs or energy per acre foot? And if so, how much?
It does not save energy. So because we have that extra pump involved, it's more, you use more energy for the process. And I couldn't give you a ballpark figure of what that impact is. It's not huge. It's a low head pump, right? You've only lost a little bit of head across the pressure vessel. But there is certainly an extra pump involved. And that's where that extra cost comes from, the CCRO.
Good. Okay. Well, that's interesting. Is that detailed in the final report?
That I don't recall.
Okay. Well, all right. So why don't we? That's the last question specifically for Eastern. Why don't we open it up to everybody? Please type your questions in the Q&A, and we'll take them. Otherwise, Don and myself, we have 1,000 questions for all the speakers. So, Megan, this next one's for you. What was your experience with the online ATP analyzer? Was it easy to use, maintain? Were the results compared to the grab samples? I think you're just curious. And Brian, thank you for that question. Appreciate it.
Sure, thank you. Yeah, so Yana Safarik was our lead scientist for the RO LRV study. So if folks have want more detail than I can provide, I'll follow up with her. But in general, I think she found it easy enough to use. It's a Hawk Easy ATP online analyzer, fairly recently developed. We've been using benchtop ATP methods for years in our research lab. And I think Yana did some comparison and found it acceptable between like the bench and the online monitor. The online monitor allows you to bring a grab sample to it, I believe. So that was handy and does require a pretty costly consumable, replacement of consumables on a regular basis. So some maintenance and consumables involved to keep that online analyzer running. So we ended up reducing, in different aspects of our study, the frequency of the online grab to save cost on the consumables, because we trying to run some cost numbers, and it really does add up over time if it's a continuous monitor on feed and permeate in the plant.
Great, thank you. I don't see any other questions from the participants. Please, this is the time to ask questions. Please put your questions in the Q&A. Otherwise, Don and I are going to pepper our victims with questions. I've got one for both presentations. Seems like the treatment trains at the wastewater treatment plants is something that we should be looking at very carefully. Megan, your study confronted that directly. Should we be approaching wastewater agencies and asking them to optimize their treatment trains for these potable reuse projects?
I can jump in for this. Well, so our study goal was specifically to demonstrate credit or removal across the existing process. And of course, we're using their existing effluents to our potable reuse facility with no problem. I mean, but in general, broadly, I would say the activated sludge process would be more recommended than the trickling filter process. We do get a lower quality trickling filter effluent in the blend, higher ammonia. So there is a current Water Research Foundation study that might be wrapping up soon that's specifically about optimization of the wastewater treatment process ahead of potable reuse and what's to be aware of. So I need to review that myself and see what some of the main recommendations were.
That is one of the studies that Metropolitan is co-funding with the Water Research Foundation. So yeah, hopefully we'll have a webinar on that when that study is complete.
Okay. And this is Dave from Eastern. Well, now that we've done this pilot and we've done the preliminary design, we are going to move into final design on a 2 MGD treatment plant. And so one of the things we are going to look at in the final design is phosphate removal, if I can say it, for the feed water. So that would definitely improve, less acid needed, things like that. But the 2 MGD is such a small portion of the plant. When the main plant is over 20 MGD, do we want to do a side stream removal, or, is it cost effective if you did it all for the main treatment? So in our final design, we will be looking at possibly optimizing it, but we're in a situation where we own both the reclamation plant and this advanced treatment plant. So we will look at that, but it's a cost kind of thing. And then also, this is a phase 1, it's only 2 MGD, it's fairly small. Those issues will become larger and more important as the potable reuse project expands in the future.
Great, thank you, David. We did have a question come in from the audience from Greg Waterow. Thank you, Greg. And this is for Julio. Julio, did you do any monitoring of the viruses downstream of the MF treatment to confirm if there's been any additional removal occurring there, or was it just focused entirely on the wastewater treatment plants?
Yeah, our monitoring was focused entirely on the wastewater treatment plant. We did not take any samples after disinfection or microfiltration effluent.
Okay. Well, I don't see any more audience questions. I think we have time for one more question, and I'm gonna, I'll take the privilege of that question, and that is, both of these pilots occurred and then COVID-19 hit, and you guys had to adjust and adapt your studies for COVID-19. I was wondering if you could share with the audience what you had to do and how you were impacted by COVID-19, and then how you responded and overcame it, because you did a great job completing these studies.
I can start this, Dave, at Eastern. Well, one of the things that we designed our pilot was for tours, and labeling everything, putting up some kind of graphic message boards, and we had envisioned doing a lot of tours through the facility. Well, when COVID hit, obviously we couldn't do the tours, so our public affairs group developed a virtual tour and posted and they made a micro website on Eastern's site that you can go on to our website and take a virtual tour. So that was one thing that was a little different. We also partnered with Cal Poly Pomona and their students to do the testing on some of the water quality, and so that they were still able to do it, but it was a lot less access, limited, and only a certain number of people at a time, and taking all the protocols. So it definitely had a more of an impact, I think, from the public access and public relations than the actual working on the unit itself.
Thank you.
Yeah, for our wastewater treatment study, we were somewhat fortunate enough in that our analysis for our cultivable virus data set didn't begin until around the time the pandemic started. So we actually had to have a shift in laboratories at the very beginning of the study, because the staff that were at that particular laboratory at Michigan State couldn't perform the hours, obviously, because of people being in the lab. So there was a pause time, and in order to catch up with that virus analysis and the backlog number of samples, and to be compliant with the time for stability, we had to switch labs to a high throughput laboratory once things got started, we were able to get all that data fairly quickly. So that was sort of the biggest hurdle for the pandemic.
Well, terrific. Great job managing everything through the pandemic. And we have time for one last question, and Ryan got it in there. So Megan, this is addressed to you. Are there any other monitoring methods available or currently being studied that appear to perform better than strontium or sulfate for log removal values for RO?
Oof, I have to look at the numbers, but there is one other main method that we're looking at in a separate study now. Backing up though, for OCWD, we are moving ahead with the tiered framework of strontium, sulfate, and ATP. We're really happy with that enhanced credit. It meets our needs. But as part of a different research study going on in parallel, we're looking now at conductivity profiling. So that'll be reported in future Water Research Foundation report. I should know the number, 4958. So conductivity profiling is a statistical technique where you're sampling the permeates from multiple pressure vessels at different stages within the RO unit and doing some complex mathematics that basically account for the fact that some amount of salt passage is expected based on the permeability of the membranes for the salt, and sort of correcting for that and calculating an LRV. And I don't recall the LRV off the top of my head because the study's still in progress and we've got lots of data, but that could be perhaps a little higher than the strontium. My disclaimer is we don't have the study completed yet. So watch out for conductivity profiling. There's a paper in the literature by Jim Vickers from SPI describing the technique, and that's being evaluated as part of this Carlo-led Water Research Foundation study, along with other methods for RO credit.
Great. Thank you for that. I think that's all the time we have questions for today. We're coming up on the end of the webinar. I want to thank Megan, Julio, David, and Christian for terrific presentations today and just great studies. They're great additions to the Future Supply Action Funding study. These studies won't help us with our current drought, but they will help us with future droughts and building resiliency to climate change as we go through our One Water approach. So thank you again. I also want to thank our member agency partners, Tiffany Foot at Fullerton, who helped manage the Orange County Water District study and did a great job also overcoming the challenges with COVID-19, and there were many. Also Bill Therensen with Eastern, who was I think the study lead there. I also want to thank and recognize the Metropolitan FSA team, Don Bentley, who was the lead for the Fulton study, Hannah Ake, who left Metropolitan but was the lead for the Eastern study, but also Matt Hacker, Ariba Saeed, Stephanie Franco, who's on the call today, also Ryan Roman, Teresa Gonzalez, and Lauren Carrillo, who've been helping out with the webinars. Without their outstanding work, the FSA program and this webinar would not be possible. So this is the last webinar for this year. We might have a couple more next year, so look for those announcements. But what a great way to end this webinar series for this year in 2021. And I want to again thank the presenters. I think this concludes our webinar. Please take care of yourselves, take care of each other, and hopefully we'll see you next year with another webinar. Thank you again for your presentations. Great.
Thanks, Warren.
All right.
Thank you. Bye.
Thank you.
Thank you.